So today, what we want to cover is that we want to cover some practical aspects of chapter 4 and some practical aspects. When I say practical aspects, I mean implementation of some algorithms which are related to chapter 4 and chapter 5. Chapter 4, it is about filtering and in the frequency domain, or in principle, chapter 4, it's how to use filters in the frequency domain. These filters, they could be low-pass filters and high-pass filters. And whenever we discuss the low-pass filters and high-pass filters in the real domain and the frequency domain, there is a very strong overlap between these two aspects. And for this reason, today we may focus on some implementation of these filters, both in real domain and in the frequency domain. So chapter 4 is predominantly discusses aspects of the frequency domain, and chapter 5, it is regarding the image restoration in the real domain, which and it's called like image restoration and reconstruction, which talks about different types of filters, one aspect which is which is more clearly explained in chapter 5 than in chapter 4 is the issue of applying a notch filter. Notch filters are filters which clean out completely a specific frequency. Now, having these notch filters both in chapter 4 and chapter 5, this brings up the issue of really, or at least it reminds us of regarding the common or the overlap between these topics. Now, for a moment, let's see. I think last time we were discussing about these images, which, as I said before, this was the image of copper, imagem e Bakrit, on a fluorescent screen, which in principle is simply the Fourier transform of this element. Now, let me see for a moment. Let me see if I can find this one. This should be somewhere in periodic noise. Okay, so let's have a look at this at the aspect of the notch filters. So for a moment, let's run this section, and let's try to read what pattern 01 is. Pattern 01, apparently it's an image which is 240 by 300 by 3 by 3, which means that this has let's do this figure 101. Let's have a look at the image itself. And this is what it looks like. For a moment, let's also have a look of how can we plot the first layer, which is the green layer, and let's call this one figure 102. This is the red. We didn't see much. Why did this happen? Because I'm doing a mistake. Okay, so in order to see the red layer, we should consider all the rows. This is how we can do this. All the columns, and the one should be here. So let's do this one, 103. So this is the red layer. Apparently, this is exactly the same like the, let's say, RGB, the green layer. And let's do this one, 104. So apparently, since this one is black and white, having this one in 3 layers, like 240 by 300 by 3, it's not really something, really a colorful image, because in principle, this is just black and white. And what we can do is that we can convert this one in grayscale. So this RGB to gray, this is what it does. We get a 240 by 300. And now let's take this away. And let's have this figure 105. let's evaluate this selection. And this is an image which was pretty much similar to what we had before. What this image has special, what is special about this image is that we see some periodic features. And when it comes about periodic features, one of the features which I like the most are these Penrose tilings. I sometimes give a homework with you working on Penrose tilings. So these are some other tilings or structures which have specific patterns. And whenever you see such a pattern, with assuming any one of the images which are shown here, wait a second, image. Black and white. So this would be better to work with. So we see some Penrose tiling, which have some level of difficulty. And these, in fact, what is interesting is that all of these tilings that we observe, they are all decomposed into small frequencies. For example, this image which I'm trying to show here using the mouse, it's a convolution of the frequencies which can be which are into making this shape here and this other shape down here. Now, this is again some periodic features, and regarding the analysis of these, let's try to find. So first of all, let's find PQ. PQ, what this function does, this prepares a matrix which is sized 480 by 600, which is twice the original image. Whenever we calculate the Fourier transform, it's good to do the padding, which means that we can provide a larger size for the image in order to find the Fourier transforms, because we get less errors. Now, we have here the image itself is 240 by 300, and now we want to find the Fourier transform of the original image IMG. What we notice here is that the Fourier transform f, which we can see down here at the workspace, it is 4 times larger in dimensions with respect to the image, because one axis is multiplied by 2, 240 times 2 is 480, 300 times 2 is another 600. So we got here the Fourier transform of this image. First of all, we transform the variables from unsigned integer a to double, and afterwards we do the fast Fourier transform. And regarding this, let's see how the fast Fourier transform looks like. Now, what we observe here is that we see some periodic patterns in this figure here, and this is logarithmic of f. Now, an almost equivalent, sorry, no, this shouldn't do this, no. An almost equivalent figure we also observe by doing this one. You can check these codes again later. And the ff, it's equal to the absolute value. So we know what f is, but let's define a new variable, which is the absolute value of all of the numbers we calculate. And when we talk about the absolute values, I want to say that, let's see, f 20 by 30, let's see what it is. The f is the Fourier transform, okay? And just a specific number in the f, in the 20th row and 30th column, we see a number which is 1 times 10 to the power 4. So this is 1,115. So this would be the real part of this complex number, minus the complex value. So this is something like this, 1,115.7 minus I, so this is the square root of minus 1, 3,567. So this is a complex number, undefined variable. Okay, we can say this one AA. Why can't we do this? Okay, minus. Maybe I need to write this one J. No. Maybe I need to write, how can we denote this one? Times J. Okay, we got a complex number, which is here AA, and the absolute value of this AA, this is what it is. So the absolute value, it's something like the the real part square plus the complex part square all square root. Or let's have this b is equal to 3 plus 4j. Okay, so here this is a complex number. Let's see what is the absolute value of b. So we get the 5. Okay, so that's what they are. So it's good to have this this intuition, or at least we should know what these little black boxes are. So we had the image, it was an unsigned integer 8, we converted it into double, we calculated the fast Fourier transform, we found the complex numbers as it was shown here, which was f, sorry, this was the capital F 2030, and then we can calculate what is FF 2030. So this is what we find. And actually, oh, it's not to scale, because initially we calculate the absolute value and then we calculate the logarithm of these values. Because let's have a look. Yeah, so that's why we see a 9 here, because it's the logarithm, but I don't know what base is this. So let's see for a moment what is log 10. Okay, so it looks like log by default. It is log with base 2, so it is like natural logarithm. So that means that log 2, this is 0.6, this is log base 2. Log 10 base 10. No, this is log 2. Okay, 2.71, so this is close to 1. So this is the e, or the exponential to the power 1. This is what, so this means that the logarithmic of exponential of 1, it's equal to 1. That means that this log, this is log base 2.71. It is not by default log base 10. That's good. So that's why that number is around 9. And then we, in figure 134, we can plot here a figure which looks pretty much the same with what we had before a while. Now, what we do now is that I put a note. So this is the image in mathematical construct. If you remember, in the last week, in the previous session, we just mentioned that whenever we calculate the Fourier transform, the first domain, we call it mathematical construct. It's all complex numbers. But now let's have a look at what the image looks like in the experimentally measurable domain or experimental construct. So let's see, actually, all of these are expected to be equivalent. So this is the first image. So we are completely blind because we have a saturation of the signal here. And because we are using ImShow. And so we are trying to show the logarithmic. And by the way, let's copy this and let's say the following. Max of these values, this is 16.09. So the maximum value that we observe here, this is what it is. And now, it's not a lot, but maybe it's just because it's a real number. Wait a second. So let's see. Okay, so figure 131, it is exactly the same with figure 132, only that we are scaling the domain that we are seeing just by using this little function, or this little squares, sorry, this little parenthesis here. And here, we notice that we can also find again another image which has comparable frequency intensity distribution. So if we see the brightness in the center, they are all comparable to each other. One thing that it's worth checking is that whenever we calculate this logarithmic value, one trick that you can use is that you can line 19 and line 20, they are almost the same, but we should never forget that the logarithmic function, it is the inverse function of the exponential, and the logarithmic 0, it is not defined. So in order to, so logarithmic of 0.0001, this is minus 16. Oh yeah, this is what we got before, yeah. But let's assume for a moment, we get minus 36, and here we get minus infinity. So in order, because you know how the logarithmic function looks like, right? It goes from minus infinity to plus infinity. with a way which is symmetric to the e to the power x exponential function. In order to remove these undefined values, it could happen that some pixels in the, so actually we did here max max, so let's try this for a moment. We said max max, but let's see what is min min. Min min, because we are working with this value. The minimum value is 2. So it's really scaled in a wonderful domain, so that we don't get these, what's the name? We don't get the scary undefined functions that could look something like this, which is minus infinity. Okay, so what is important for us is just to notice that these features that we observe here, they are the Fourier transform of the original image, which we can see, we can observe in here. So this is the original image, 240 by 300, and here we have the Fourier transform of this one, which is 4 times larger in the number of pixels, and we notice that we have some periodic features which are represented as bright spots wherever we're trying to show with the mouse. Now, we said from the last time that always in the Fourier domain, everything is symmetric with respect to the center. Now, the brightest spot is right here in the center, and let me try to have a look at this data cursor. So data cursor, this is 0. So this is 111. So this is bright. When I say bright, this is the highest possible intensity. So we are reading something around 1. Let's move this way, and it looks like the next bright spot, it has an intensity of 0.90. I'm not sure if you can see this one. I'm not sure if this is good quality enough for you to see this one, but I can read this. And also here, it looks like the next bright spot, it has an intensity of 0.83. So, and let's go down here. This is 0.88, 88, 89, 89, 86. So this is 0.89. The symmetric domain on exactly the other side is 0.89. So the brightest spot is right in the center, as we were expecting. This is saturated, it's 111, because it's scaling everything 0 to 1. Now, these values that we observe here, let's not forget that we got this graph by doing the shifting. So why did we do the shifting? Because before doing that, we had figures that look like this. Now, this figure 12 is before doing the shifting, and we can observe that here the data cursor, the highest pixel intensity, can be found, right here. So this is 111, okay? So 111, which is located at pixel 11. After we do the shifting, this domain, which is the first quadrant, which is here when I'm trying to read these values, this will be immediately be shifted down to this quadrant around here, okay? So we said last time we can draw a XY coordinate system in the center, and we just shift the first quadrant with the fourth and the second with the third, and this is what we observe. And then, so far we're just having a look at what we're obtaining. Now let's move ahead and let's try to filter out some of these frequency patterns in the image that we are working with. One thing that is tricky is the aspect of where we are going to apply the notch filter. The notch filter, it is, let's see, so this construct, these values, actually I don't remember exactly where these frequencies, okay, I believe this is the width of the function. So this is the 40, it is the width in Fourier domain, and these two coordinates, these are the coordinates where the notch filter should be applied. So for a moment, let's have a look and let's find the brightest spot here. This is 0.83, 83. So it looks like the brightest spot is here. So this filter, we have to implement this one we have to apply a notch filter, which is apparently we've done a good job here, because we have applied a filter with a width of 40 units, 4826. Maybe it's best if we do this one 4926. So let's do this 4926, and let's have a narrower filter. Let's make this 10, and let's come up with a notch filter H1, which now appears in this graph here. Now that we have this H1, we can try to plot what H1 looks like, and let's have here figure 22. In show, we have filter H1, and this is what it looks like. So this H1, this is a notch filter because it is 0. So what this is, it's in fact 0 right at this specific value. Okay, so which is at 4926, whatever it was, 4926, yeah. And we assigned, let me see for a moment, we assigned the thickness, not thickness, but the bandwidth of 10. So this is, let's have a H1 11, and let's have a bandwidth of 2. Let's see what we observe. H11, evaluate the selection, and then we say this is H11, figure 222, and we can see that this one, it's a narrower bandwidth in the frequency domain. Okay, let's not forget that this we are constructing a filter in the frequency domain, so it's a dark spot. But in fact, if you want to see a three-dimensional, wait, how can I do this one? Do this by doing surf L223. This is H11. Okay, so wait a second. So let's do this again. So this filter we are constructing in the Fourier domain. That's where it is. So it is located very close to the 0, 0. So this, wait a second. So let's try. Actually, if you look at this from the top, it's easily seen that this is really close to the 0, 0, which is in fact this coordinate here, 4926. And then we can see that this is a filter which is going to multiply with 0. You see the bottom, this one is 0, and the top is equal to 1. So multiplying this this mathematical construct, let's call it this way. So this is one way, this is a mathematical construct, which if we want to filter a specific frequency, and if we want to clear out if we want to precisely clear out a specific frequency, we need to multiply this this mathematical construct data with a filter which is 0 exactly at this point. But one thing that we can add is that if we want to remove this specific frequency, which is right here, we cannot remove it completely by multiplying with 0 only this point here. We have to multiply with 0 also this other respective domain, because this point, this has so this frequency is like a vector which has a projection along the kx and a projection along the ky. Okay, the same way that we have vectors in the xy domain, and yeah, so this is how we can say this. So apparently we made up this this filter H11, and for a moment, let's see. So we have f, right? And let's multiply this for a moment with H11, and we have image filtered 1, evaluate selection, and image filter 1. How did we plot these other ones? We used to say we did im show, right? Yeah. So then, in fact, let's do it from here. So this is im show log im filter 1. Okay, so this is it. The only thing is that we multiply this one with such a narrow filter that we almost don't see this. So if we zoom in a little bit here, so we have multiplied with a notch filter which shows a pure zero right at this spot. Okay, and this is what we observe, but probably we are not cleaning enough frequency terms. So probably having not a filter H11, but having this other filter which was H1. If you remember, we implemented this was H1 because this was wider. This H, where was it? So this was narrow, but this looks like it's really diminishing a very small amount of frequencies. So probably rather than, sorry, where was it? So we made H11 filter. Let's multiply this one with, sorry, H1. And let this be 2. Evaluate selection. Again, we don't see much. This, it looks like, oh, maybe we are plotting on the top of the same figure. Let's change, because before a while we plot this one on figure 14. Let's see. I was expecting this one to be a little. It's not bad, it's good. But I want to see how much this has weakened the. So apparently we could even work with larger filters. The last one we used 2. Let's have here 40s at these specific locations. And again, let's have a look. If we want to clearly wipe out this frequency, let's look that we have to read 8353. So this looks like 554. Let's see, probably I have these numbers here. 554, 456, 456. Yes, that's true. So apparently H1 and H2, they correspond. So in order to clearly wipe out completely a frequency, we have to generate 2-notch filters, which are going to select, let's say, is going to wipe out this one and this one down here, which on the other, in the experimentally measurable quantity, that's the term I like to use in this course, is that we will be able to clear out data cursor, this spot, and this one. And since we have them right here, so actually wiping out this one here, this one, which has coordinates of 49, 26, here in the experimentally measurable figure here, this 49, 26, it is equivalent to what we see right here, okay? Why? Because we do the shifting and a spot which is around here will be immediately brought down here. And at the same time, this spot, which is bright and is in the frequency domain, this corresponds to this other side. So again, this one is symmetric with respect to this, then this frequency. So actually, this axis ky bosh këtu është kx dhe kjo është ky. Me k interpretojmë boshtin e frekuencave. Again, so this was some theoretical aspects. We generated all of these filters. It looked like the coordinates that we have here, they are correct. Let's generate once again all of these filters. If we want to have a look at these filters, how they look like, we have figure 119, and apparently this is what we get. So now all of these filters, apparently this is H1. So H1 and H2 are clearing out this frequency and this frequency. H3 and H4 are clearing out this and wait a second, this and this. So we're trying to clear out this spot and okay, and this spot. Maybe it's better to have a look at these terms, because H3 and H4, which are at the edges, what they are trying to wipe out using these notch filters is this one and this one. In fact, it's good to mention this one, not to mention, but to compare these notch filters with the terminology of the frequencies of light. Notch filter is the same way of trying to wipe out completely one frequency. And this frequency, if we think those in terms of the frequency of light, imagine ultraviolet, drita diellit ka UV, UV, ose dritë ultraviolet, xhami dritarëve e thith në mënyrë perfekte UV-n, që do të thotë kjo na siguron neve po të jemi brenda shtëpi me xham. Pra, sepse ultravioleti shkakton kancer lëkure, po të shkojmë plazh për një kohë të gjatë, mund të kemi skin cancer, which is common for surfers or they stay in the beach for a long time, but it's not that scary like other types of cancers. But what happens is it is UV. So in this case, we can interpret that the glass, it's a perfect notch filter by removing precisely the ultraviolet frequency that is in the natural light of the sun. Now that we are dealing with coronavirus, it is good to open the windows with no glasses, because this way UV light will come in and probably it might kill the bacteria or the virus, the COVID-19 virus. So so this UV, it might be desirable in the case where we are really interested into wiping out, let's say, specific bacteria that can be endangered by specific frequencies. Okay, so 3 and 4, as we said, they are trying to wipe out this point and this point. And then we have these other dots around here. So apparently we're trying to wipe out, I believe, some other spot, but right now I cannot read it precisely. But let's move ahead and let's see what we observe. So now we have here, let's see, the image filter that we want to filter. Let's change the name as it was before. This image that we want to filter is equal to the mathematical construct tool, which is the F, multiplying it with filter H1, multiplying with H2. Why do we have H2 twice? H2, H2, so let's take this away. This is H2, H3, H4, H5, H6. Okay, and then, so after we multiply this one, let's see what happens with these in the, okay. So it looks like we try to clear out some frequencies, but before that, let's see what they really are. Well, let's try to identify what they correspond to. It looks like we may need to redo these again, because I cannot identify precisely what these are. So let's read for a moment. Toolbox, so we said that this is gone. Let's try, this looks like a very bright spot. It's strange, why is this so bright? This is 0.82, 0.84, 0.84. So let's clear this one. 124, 27. 124, 27. And this one, this is the reciprocal of this one. So this is 458, 455, 458. Okay, so far we're trying to remove this and this, but then what else would we want to remove? Probably this one is also a very bright spot. So let's take this one also. So this one, 0.83, 87, 87. Kjo është Nasıl yer peste Nasıl yer peste and then we get the corresponding symmetric one. 0,7, this is 5.6 430. 5.6 430. Okay, so we are kind of generating this again, and then so yes, we try to wipe out these three dots. Okay, so we really can see that they are diminished, or at least the contribution that could come from those is going to be equal to 0. And then once we do this, what we can do is that this image filter that we wrote here, this, let's put here image filter 2. We take the inverse Fourier transform, we find the real part, and this would be the image clean. And let's see what this image clean really does. And it looks like our image, it is drastically different from what we had initially. And one thing that it's strange is that the image that we want to obtain, it's shown like larger, because let's not forget that the image initially it was 240 by 300, but now we are only operating with 480 and 600. So in order to see the image that we are cleaning in the frequency domain and we are observing in the real domain, let's crop this one and let's evaluate this figure 16. So figure 16, this is what we observe. Now the original image, let's not forget, this was figure 107. So we started with this image, and by filtering those three specific frequencies, this is what we observed. So we really diminished the frequencies, and very little information is left. If you want to clear out some more terms, what we are going to need is that we need to wipe out some more frequencies. And in order to do this, let's have a look of what could be good spots to remove. So we said that we removed this, and this one here. Now, another interesting spot which could be worth taking it away, it looks like we can try this one. So this one, this is 75. This is 4877. 4877. And here the reciprocal of this one here is going to be this spot, which is pesine peste 4, 4 pes. Pesine peste 4. Pes. This is going to be H7, this is going to be H8. So we have two more filters, evaluate selection, and then here we just need to multiply again by H7, multiply again by H8, and now let's call this one image filter 3, and let this be image filter 3. And let's see figure 144. Okay, so we have wiped out some more frequencies. Of course, taking out something like around here, it could also be very useful. but at least we see that we have really removed major terms. Now, it could be a good exercise for you would be the following. You may assume that you may clear out only the frequencies at the top corner right here and not clear out these frequencies down here. And you are going to see that your contribution will be null. So you are not going to do whatever you are supposed to do unless you remove everything. So this is image filter 3. And let's calculate this image filter 3, image clean 1. Let's call this one image clean 1. And let's plot this on figure 151. Okay, so it looks like we have not removed much. This is image clean 1. Okay, now it remains for us to compare whether there is any major difference between these two. So the last figure is 161, and by human perception, we might not do a very good job here. But what we can try here is the following. We have image clean and image clean 1. So we can try the following. We can say figure 162 im show image clean minus image clean 1. Let's not forget that these were the two subsequent outcomes when we were cleaning the data in the frequency domain. And let's make this figure 162. Okay, so it looks like there is a difference between these two figures. If there was no difference, we would get here all zeros, and it's really considerable difference. In fact, let's do also this. Oh, okay. So this is really the difference. So it looks like this frequency that we removed, the latest one, which was, so it's carrying this much information. It's huge, actually. You see, this one in the real domain using filter H7 and H8 versus not using it, it is going to be this much of a difference. Okay, that is interesting. Okay, so this is how we can analyze our display the Fourier spectrum, move the origin to the transform. Okay. Again, okay, so with this, let's see what we observe here. The directives are already provided, evaluate the selection. So figure 17, this is the F. So this filter that we have cleaned, which is now, let's not forget that F, let me see it, where is F? No, the F is the original image, so we have not, F is in fact the, okay, that's what it is. And then this is the shifted after the Fourier transform of the image is found. Okay, so this is not filtered. This is just the original F. But then this F, this is shifted after we filter it in the frequency domain. So let's see, evaluate selection, figure 18. So figure 18, this is what it is going to look like. So we have zeroed out some terms. But again, I see that there are some mistakes here, not mistakes, but why do we see these black spots here? Use absolute value to compute the magnitude and use the log to brighten display. Okay. Again, in fact, evaluated selection. So this is the difference between the original image. Wait a second. I can show it to you what I'm trying to do, but probably no. Okay, so in fact, this would be a good exercise if you go after all the steps that are explained here step by step. We made a difference into the code by adding these two lines because we wanted to filter something more. And let's comment this and let me have a look. So what can be done if you watch carefully is that we defined, so this f new, this is the difference between the original image that we had at the beginning minus the unsigned integer 8 type of variables after we have this clean image clean, okay? And if we subtract these two, we observe this im show f new. Then this f new, what we are trying to plot here, we are plotting po plotësojmë rrjeshtin e 29 tek matrica f new. Pra figura 22, let's have a look at figure 22. Figure 22. No. No, figure 22 is this one. But before 22, what did we plot? Before 22, we plot 21. Where is 21? No, 21 is this. And 21, in fact, we see that even after the filtering, we still have a lot of features. And in fact, this figure 22 is just the, how can I say, the 29th row on this matrix, okay? So 29th row, we see that the pixels can go up high around 200, which is some bright spot. They go down to 0 or 5, which would be the dark spots, which are shown here in this figure. Now, this one, it's really something which is, it's some periodic noise, which is often used in textile. If you have some more elegant noises, you might observe interesting functions here in line 80 of this code. As an exercise, what you can try to do is that you can pick up different pen row stylings and see what you observe once we conduct these types of filterings. Okay, so this was something regarding the periodic noise, and then what we May 13. I have also some interesting aspects. So let's see. This is very similar to the other example we just did. This is May 5, and for a moment. So let's close all the figures we had so far. Apparently, we have another. Now, this one, we're not going to do this one step by step, but let's try to observe what happens. So we have some money here, which has some noise. When I say money, this is some old banknote of Albanian bank. So this is 50 lek. With this much money, you could have a very nice time for over a month. A few decades ago. Now, let's see, here we have K, as they know this evaluate selection, and let's bring up a function, a filter, which is very good, which is the Butterworth filter. We have also ideal filters, Gaussian filters, but this is really good, the Butterworth. Ideal filter is a filter which is like a step function between 0 and 1. It is not very reasonable to have such a filter, because filters in the frequency domain, it is best if they are smooth. So this one, this is, we can say, bad because it is not a smooth filter. This is good because it is smooth. And this one is slightly better than the Gaussian, but let's see what we observe. So we generated, wait a second, we have not, let's, and to have the Butterworth filter, we need also a value of P. Now here we can generate the filter H. And now to have a look of how H looks like, here we have it. So figure 1, it is, so it's something like this. The top view, it is 1 at the center, 0 at the corners, and these are, wait a second, so these are the, yeah, the Butterworth filter. Now image, let's see what we observe. Okay, so we have only one filter, and this filter, it can evaluate selection. So now let's see this noise. Okay, so we have this money, which has apparently it has some noise, which is periodic noise because we see some frequencies here, 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 and here. And in order to filter out these components, what we can do, tools, data cursor, is that we can multiply with a notch filter right here, another notch filter right here, one here, and one here, and we can remove the periodic noise. At the same time, what we can do is that we can multiply by a filter, which is like a Butterworth filter, which is this. What this filter is going to do is going to multiply with 1, whatever is around the center of the image, and multiply with 0 everything which is out. So we're going to get 0 artificially, okay? And this filter, this is done right here. So let's see how, sorry. Wait a second, figure 14, it is the filtered image. Figure 15, maybe we didn't let it plot probably. Figure 15, okay, so everything, we have wiped out too much information. And this is just the very weak contours of the original image. Now with this one again, you can test at home by experimenting with other images which have periodic noise. I want to show something else, which is next. Evaluate the selection. Let's see. Okay, we'll clear everything. Wait a second, this is... In fact, let's try to see what is this. We have, we can construct a matrix which is full of zeros. Okay, so here we have another figure, which we construct this one artificially by having a matrix 200 by 200, and then all the rows in the, or wait a second, all the rows with columns with a difference of 40. So we do this, the first column, the 40th column, the 80th column, pra 20, 20, 80, 120, 120, 160 dhe 200, këto bëhen gjitha nisha. Pra kjo është ai nishi që shikojmë ne këtu. Ndërkohë, përgjatë radhëve, along the rows, every 10 rows we make ones. So that's why we see here that we have more horizontal lines than the vertical lines. And then apparently we make up an image which is I1. Now we see that there is a periodic noise, but there is a specific periodicity along the x-axis, and there is a specific different periodicity along the y-axis. Now the difference in the period is a factor of 4, because here we see that we have a line of ones after every 40 pixels, and here we have a line of ones after every 10 pixels. Then we looked, we saw what happened, and then immediately we just calculate the Fourier transform using line 63 of the code, and in line 64 we just plot the Fourier transform, and this is what we observe, okay? So we notice that along we have one specific frequency. Along the x-axis, we have, let's say, a small frequency, we can say. Along the y-axis, we have another frequency. Now, if this was a square here, we would also observe as equal k vector spacings, okay? So again, kjo është boshti x horizontali, kjo është boshti y. Këtu kemi boshtin kx dhe ky është boshti ky që shikojmë ne këtu. Okay, now this was an important example. Other things, so now these other codes, you can also check what happens to the frequency domain if we rotate the images. Wait a second. I don't want to run all of them. Okay. So this is something different from what we observed before. And one thing which is also very, very interesting is that in this image, we observe two frequencies. So we have a repetition of the vertical lines after every some distance, which is 2a. And actually, we can even have a look here. So it looks like d is equal to 40. But why do we get this? So we're seeing that we're going from 1 to 40 plus 40 plus 40. Okay, this is something tricky. So this is even some problems, some visual problems, which, okay, so also here, apparently, if we stretch this one out, why can't we see this? So if you get a little closer, initially we thought as if some frequency was missing. I'm not sure if you share the same concern with me, but here it really looks like, at least to my eyes, that we have some non-equal distribution of the bright spots in the Fourier domain of the frequencies along the x-axis, or along the kx and the ky. But now, if you zoom this one out, this is what we can observe. Now, let me see. Now, all of these examples, which are examples of constructing periodic noise, you can work with this again. Now, this periodic noise or periodic features, they or at least the approaches that we used here, it can be used in some very smart measurements. For example, we had a data set of images, of cell images, which I'm not sure if I can find one right away. How should I find it? This is going to be It takes some time. Okay. So let's see an application of these periodic noises. So we have a paper here which we work together with some of our collaborators, where we have studied, at least from the image analysis perspective, of how we can analyze the images if we remove some periodic noise. Now, let's first of all, let's report what is this periodic noise. Regarding so these images, they are still images obtained from microstructured surfaces. So, or micro-pattern surfaces, this is a better word. And micro-patterning, it is very important, especially when in biomaterials. So even if you have a tooth implant, for example, you have a problem with your tooth and you put some implant in there, often these implants are not smooth. They are not perfectly smooth. They have ridges, relief, they have texture. We can call them a texture. So if you touch them, you can feel that there are some micro patterns or there are some lines. And now we had some so researchers, what they are doing is that they are constructing micro pattern surfaces which look like this, and they want to see what is the effect of the micro patterns on the life of the cells. So these cells that we see here, there are some they are called THP macrophages, and what happened is that in order to study the micro patterns, what they do is that they grow a film, and this film they can structure it. What they do is that once they build the film, so this one, it has no patterns at all, this unpatterned. Then we can have grooves in the order of 2 micrometers. Then we can also have grooves in the order of 20 micrometers thick. So we can make tunnels which are është sikur me marrë një copë silikoni ose një gjë të butë, edhe ta gërvishesh me thonjë, por distanca të bësh kanale, ku kanalet mund të jenë larg njëra tjetrës në rendin 2 mikrometër ose edhe 20 mikrometër. Kjo është problemi. So these biomaterials, they can have ridges, they are not perfectly smooth. These biomaterials can be a tooth implant, it can be zirconium, it can be trisma, it can be Admira fusion. These are all dental materials, but at the same time, these patterns, they can also be used whenever we use an implant in the bones or in some places where there is direct contact with the tissues or with the cells. Now, cells and tissues, they react differently to micropatterns, and that's why we want to study them. Now, our task, it was to quantify the number of cells as a function of time, and the time, it was equal from 2 days up to 20 days. So we wanted to quantify how many cells were alive and how many were not. And the images, they had ridges or these channels, and the point is that these channels, they are in the order of 20 micrometers, and this is the size of the cells. The cells can be as large from 10 to 15 micrometers. So what can be done is that so in principle, this looks like whenever we try to detect a cell somewhere, we might be fooled by the contour which is constructed by the edge of the ridge. Pra, këto kanale që janë, distanca midis kanaleve është 10 deri në 15 mikrometër. Kjo është madhësia e qelizës. Pra mund të ndodhë ndonjëherë që konturi jashtëm i murit mund na mashtroj, sikur të jetë qelizë, dhe mund të numërojmë, we can count false positives, etc. So what we did here is that all of these images, we calculated the Fourier transform, we applied notch filters, so we removed those filters, and then we got, let's say, we got an image with no ridges, and it was easier for us to quantify the health state or to quantify the number of cells that were present in these images. And here we also quantified the levels of false positives. So it looks like whether we had patterned surface or unpatterned surfaces, we can sometimes we can observe a high percentage of false negatives. and sometimes we can have a high percentage of false positives. Now, all these tricks, it was we implemented these interesting approaches of trying to filter the images from the periodic noise. In this case, it was not a noise, it was intentional structures or intentional microstructures. Okay, so let's see again what we see, what we have next. So that was just one type of implementation. Let's see what images we observe here. So last time I believe we talked about such an image, and this one it has different frequency components starting from the center to the outer edges. We observe that we have higher and higher frequencies as the radius increases. Now, what we want to do here is that we want to observe how we can filter specific frequencies by, so let's see, we first read the size of the image I, mn, they are equal to 597 by 597, but this is something we could also see right away at the size of this I, which we read it using line 183. Then we need the value of k and p, because the k and p, they are the parameters which can be used for the Butterworth filter. And the Butterworth filter, it is very similar to a Gaussian filter, and the ideal one, it's very unique. So now we have the k and p. Let's generate a filter H, which is but this is a low pass filter. Wait a second, mn, kp, this is Butterworth, yeah. And then so this was the filter in the frequency domain. Now let's not forget what is I. I, it is unsigned integer variable. So this is what I is. And then this unsigned integer, we convert this one into double. So yeah, we convert this into double, and then we apply the fast Fourier transform, and we get a variable capital F. And then if you want to see what this capital F looks like, this is what we observe, okay? So those frequencies, they are seen here, and we have not shifted this yet. Let's see if the image looks slightly different. Okay, so after the shifting, this is what, but wait a second. Did we do the shift? Okay, so it looks like the shift is right here. So this is the Fourier transform, or using another terminology that we like to use it, which is this is the real image, and this is the experimentally measurable Fourier transform of this image here. So here we have a large dot, and this large dot, now this corresponds to this feature that we have at the center. Now let's take this away for a moment. So this was the shifted, which we plotted using line 201, and then we can now multiply the, and by the way, we have to look also what is H. So we can multiply evaluate selection. We find the image which is filtered, and this is figure 14. Apparently, we have used, so it looks like we have filtered this one, but we have filtered with a very wide filter, because we observe that there are some decreased intensities around in these edges. So let's have a look here. Data cursor. The intensity around here, this is around 0. Let's say 0.15, 0.17. But if we go here, data cursor, this is 0.21. So we have kind of, but this looks like we have decreased the pixel intensities in the edges here, because we have a very wide filter. Probably we should use something which is narrower, but let's leave it like that for the moment. So once we filter this, so this is the filtering is done right here, and then we plotted it. Then this filtered construct, we do the shifting, we take the inverse Fourier transform, and we try to find what is the image which is now cleaned from these frequency terms, and this is what we observe. Okay, so there is a considerable difference from the original image, but we see that we have done some non-zero filtering. Now, the same filtering, it can be done by implementing also this other function, which is DFT filtering using the image I with filter H. Let's evaluate this. So again, what we see here is that actually we defined the filter H. This was the image I, and with this function, we automatically implemented the filtering. What we did here, we did it step by step. We did not implement it right away. Is that we constructed the filter, which was a Butterworth filter, and then after constructing this filter, we multiplied the filter and the data in the frequency domain, because this filter is in the frequency domain itself. And after we did this, we multiplied by the inverse. We did the inverse Fourier transform, and we brought the data set in the real domain. Okay, now you can experiment with this one a little further. And now this, if this was more or less what we see in chapter 4, which was the analysis in the Fourier domain. But as we said, we have skipped some theoretical aspect, and we are just having a look at the implementation of the algorithms that we see here. Now, let's see some other examples on from chapter 5. And chapter 5, it is image restoration and reconstruction. And let's have a look at these. Chapter 4. This is chapter 5. Okay, so this is wait a second. This is okay. So whenever we discuss about image restoration and reconstruction, what we have is that initially we have some function f or some data f. In this case, it could be an image, of course, and then this f we apply a degradation function h. So so this means that the image got worse. And then after we do the degradation, we can also add some noise, which is added as using this addition function. And then afterwards, we apply a restoration filters in order to get some f star xy. Now, so let's say we degraded, we added noise, then we try to implement the restoration filters, and we hope that the final result that we see on the right side of the slide is as close as possible to the original image, which is fxy. Okay, that's what we hope for. Then, wait a second. So this was an example. I think we observed this in the when we were doing the exercises. We observed these, but we can skip them now. And here we see another example. And the code is here on the slide. You can also try to run this and try this one with different images. So apparently we have an image, which is an image of a farm. We convert this one in a grayscale, which is the fourth line here in the figure. Figure 3, we're just plotting it. And then we can calculate the fast Fourier transform of image I1. Then we can shift it, and this should give for us the Fourier spectrum, which is the second image. But after we calculate the f1, which is the fast Fourier transform, we can also implement, not implement, but we can also apply a function which is the angle. This angle, it gives the phase information. Now, it is good actually to have a look at what this angle finds, and the implementation of these angles. It's good to look at the how this runs step by step, because this can teach us a lot. And actually, let's do this like this. For a moment, let's assume that we have a, let's do this clear all. Let's have a data set which is a random number generator 4x4. Okay, and so this is our matrix. It's not an image, but it's there. We see some random numbers which are AA. And then the next step, what we want to do is that we want to find F1, which we use the Fourier transform initially and the shift. So let's say this is AA, Fourier transform, and then shifted. This is equal to FFT shift, okay, of the FFT2. So we need to do the two-dimensional Fourier transform of the AA. And this is this variable, okay? So this is again, and the size of the AA Fourier transform and then shifted. The size is 4x4, the same size that the original data set was. Sorry, this was A. So they're both 4, 4. But then let's have a look again at what this data was. So now, okay, so this is what it is, which is equivalent to what the F1 is given here. And if we plot the absolute value of and the logarithm, we can do the following. We can say, but we will not see anything. Figure 11. We can do here imshow of the logarithmic of the absolute value of f1, logarithmic of the absolute value of AA, its Fourier transform and shifted. But of course, we cannot see much because a 4x4 pixel, it is not much information. In order to see something on the screen, actually, we are even seeing more than I was expecting. So this is the Fourier transform of this data. Now, of course, this doesn't make much sense, but what I find it more important is the following. So let's calculate what is the angle. Sorry, this is what is the angle of AA Fourier transform shifted version. This is what we observe. Now, for a moment, the angle, what this corresponds to, it corresponds to the quadrant in the two-dimensional space of where all of these numbers belong. So, for a moment, let's see. What is this number? What does this correspond to? This looks like this is some pure complex number. If this is some pure complex number, that means that this complex number where it is equal to minus I. This minus I corresponds to an angle of minus 1.57. 1 pi, so let's see, pi is 3.14. Pi divided by 2 is 1.5708. So this is minus pi over 2. So this means that we find this number of minus 4i along the y-axis, okay? So this means that we are finding, where do we find this number? This number, it corresponds to an angle of minus 90 degree, or minus, yeah. And also, let's have a look at this number. This number is a pure zero. That means that we can find this one at an angle of 0. Here, this is a pure complex number, but it's positive. So the angle now, it is 90 degree, plus 90. So these are given to us, the angles. Now, another interesting trick that can be often done to compare different data sets, it is going to be similar to these. And in fact, what we can do is the following. So we have the angles, and we can do the following for I equal 1 to 4, for j equal 1 to 4. If answer ij smaller than minus pi divided by 2, then we say answer this is ij, this is equal to 8. Let's say 8 and index. Okay, so it looks like we did not do a good job. Why? Index exceeds matrix dimension. Czego bimy bałtuny? Oh, okay. Yes, we made a huge mistake because not the answer. Let's do it right here. No. Se copiou do tão. Made a mistake. It should not be answer, but it should be AA. Fourier transform shift. Okay. AA Fourier transform shift. Here we have it. And for a moment, let's run also this section. So we run this, and it looks like we said that if the, oh no, we made another mistake. We keep doing mistakes, but not, it's okay. So we checked whether these are smaller than, of course they're going to be smaller than minus pi over 2, but then, okay. What we should have done is the angle. We should have checked whether the angle of these is smaller than minus pi over 2. But this means that okay, let's randomly generate this again. We've got the AA, and I use a very long notation just for the sake of keeping it clear in the code what this variable is about. Then for a moment, let's say that BB, this is equal to AA Fourier transform shift. This is BB, and then it's going to be easier for us that this is going to be BB. Okay. Okay, here we got it. But now, is this good? We checked whether the angle, it was less than minus pi over 2. AA, Fourier transform shift. Okay. So, what is this value? Kjo është minus 8. Minus 8 të boshti XY është këndi minus 180 gradë. Pra, ajo që ka bë kjo do të thotë që këndi i kësaj është më e vogël se vlera caktuar për atë bëri 8. Ndërkohë, kjo vlera e dytë këtu, kjo është, nëse mendojmë për një moment çfarë kuadranti është në numrat kompleks, është numri -2i. Çfarë mendoni ju? I forgot asking you questions. Ky numri që shikojmë këtu, -2 -2i, çfarë kuadranti është? Nëse kemi të bëjmë, keni ndonjë koment?
Tek i treti?
Eksakt. Te i treti. Po, kjo këtu është te i treti. Mirë po, kur është tek i treti, kjo do të thotë se ka x-in negativ, y-in ka negativ. Kur është tek i treti, çfarë këndi është kuadranti i tretë? Relativisht me boshtin e x-eve. Është më i vogël se minus 90 gradë, apo jo? Pra, po t'jemi të kuadranti i katërt, bëhet fjalë për kënde nga 0 deri te minus 90. Jemi dakord? Po t'jemi të kuadranti i parë, këndi është nga 0 te 90. Po t'jemi të kuadranti i dytë, ne jemi nga 90 gradë deri 180 gradë, dakord? Por, nëse jemi të kuadranti i tretë, këtu kemi këndin që është më i vogël se minus 90. Pasi këndet e katër kuadranteve nuk quhen nga 0 në 360, por quhen nga minus 180 deri në plus 180. Tani, këtu ne po shikojmë një shembull shumë interesant, pasi kjo lloj analize e këndeve të transformimit Fourier të një të dhëne është një metodë që përdoret shumë në pattern recognition dhe është një ndër gjërat më të zgjuara për cilat duhet të kesh goxha intuit të zgjuar që të shkosh dhe të përdorësh këtë teknikë. Ne kemi pas disa problema të bukura këtu në departament bashkë me kolegët dhe sa që kemi dashur të krahasojmë për shembull datasete të ndryshme, sepse po e përmend këtë aspektin që po flasim për momentin, jo kot, por shpesh mund t'ju duhet dhe mund t'ju duhet shumë dhe mund të jetë një ndër zgjidhjet më të zgjuara për të përdorur. Pse po e them këtë? Sepse kjo në esencë çdo numër kompleks të cilin ne e gjetëm, kjo i korrespondon që këto numrat kompleks i përkasin një kuadranti të caktuar në hapësirën komplekse ku kemi 4 kuadrante. Ku boshti i x-eve është numër real, boshti i y-eve janë numrat kompleks. Por kjo -2 -2i-a, kjo do të thotë që është diku, në fakt çfarë këndi është kjo? Kjo është këndi minus 45 gradë. Pra është këndi është 45 gradë përtej minus 90-s. Besoj jeni dakord te kjo pjesa. Pra këtë e identifikuam si një edhën që ndodhet në kuadrantin e tretë. Edhe kjo me që kjo është 8, edhe kjo është kuadranti i tretë. Edhe këtu pasim 2 kuadrantet e treta, po t'i konfirmojmë me të vërtetë ashtu duken, sepse e ka dhe x-in dhe y-in negative. Pra po gjejmë goxha edhe këtu pasim 2 numra, të cilat janë në kuadrantin e tretë përsëri. Është e vërtetë, ja këtu i paskemi. Jo, këtu paskemi problem. Kjo nuk është e vërtetë. Pse e ka qenë 8 kjo? Se kjo është -5 plus 1i. Kjo -5 plus 1i, kjo është e kuadranti i dytë në fakt. Pse na e ka qenë 8, unë këtë se di.
Po dhe e para ashtu është -8 0 plus 0.
Po jo, e para është -8 është kjo -8 është te kuadranti mund të quhet ose i dyti ose i treti në fakt. Më kupton? Sepse është -8, kjo është si më thënë është tema tanë. Por kjo është e kuadranti i dytë. Dhe kjo është -5 plus 1i. Pra imagjino tani sikur kemi pikat e koordinatat x, y, kemi -5 dhe 1-shin, kjo është me të vërtetë mbi boshtin e x-eve. Këtë se kuptoj për momentin, pse na del kështu. Po le ta shikojmë. Këtu me të vërtetë pasim dyshime, pse kanë thirrë të kështu, po nuk e di pse vallë. Okej, tani në mënyrë pra ne identifikuam 4 vlera që në hapësirën fazore ndodhen në kuadrantin e tretë. Njëkohësisht mund të analizojmë çfarë janë këto vlera të numrave të tjerë, cilat prej tyre në kuadrantin e parë, të dytë, të tretë dhe të katërt. Dhe pasi të bëjmë këto lloj krahasimesh, ne për të krahasuar dy datasete duhet ose është shumë it's a very smart approach to compare the phase information. Okay? So why is this useful? Let's think for a moment that you are trying to use pattern recognition. And pattern recognition, let's assume that this pattern is an image. You take an image which is in the morning and there is too much light of your home. Bună fotografici piece, nu yes, ca și un drip. You do another image, you take another picture of your home from the same position, but when the light is darker. Now, these two images, based on the pixel intensity, they look very different. Okay, so if you want to implement an algorithm on pattern recognition, you are automatically going to report that they are very different from each other. Okay, this is if you are using only pixel intensity information, but even if the light is darker or brighter, one thing which is always the same is the frequency components. What are the frequency components? The frequency components, they carry the information of where we have edge information, okay? So that's why, and how do we get the frequency components? By applying the fast Fourier transform function, okay? So you can get all the frequency terms. And then if you want to compare your picture of your home done in the morning and the picture of your home done in the evening, what is never going to change is the frequency components or the phase information. So what you can do is that you can take the Fourier transform, you can determine which quadrant fall every element, and then you can compare those, okay? So what I mean is that, for example, and probably I can assign you a homework regarding this, but this is a very smart approach which can be understood in detail once you know how the Fourier transform operates in detail. Okay. Now we came to this problem because we were talking about the frequency components, and okay, and here I can put also another hint. You have a homework, so you had the homework 2, which was due today, but at the same time, I have assigned homework 3, which is due this Friday, okay? And in that homework, actually, what you are expected to do is just, you are asked to do labeling, which is just kind of a tricky job to do, but my objective is not to have you just label those images. Okay, I've sent you some images which are medical images, or there are some cells which are obtained at some specific treatment. What I want to see from you is that after you do the what's the name, the labeling, I want to compare all the labelings of the students in the class. So after you do that, I'm going to share with you all the labels that you have obtained. This means that don't submit 100% correct or similar labels, because the probability is going to be relatively small. And after we get different labels from different students, we are going to find all together what is the variance when we are trying to see these differences. And other than this, we want also to compare the similarity between different images, okay? So these little tricks that we have learned today, you're going to implement on the data set, which it should be ready from you by this Friday, okay? And once we have this new data set by this Friday, for next week, you're going to have another assignment. When I say assignment, so we can build up an assignment based on the data sets that you're going to prepare. Okay, so these are some important aspects of what we said of the Fourier transform, which is a technique, it's a tool, a very useful one. Now, do you have any question from what we did so far? If not,